What is it?
Recording.
Okay. Welcome, everybody. I am so pleased to introduce Dr. Diego Novosel, who's a good friend of mine and a colleague. He agreed to come and give this presentation today. I will just read a few lines from his biography. It's a long and impressive biography. I'm pretty sure you had a chance to look at it. He is currently president of Quanta Technology, which is a consulting and R&D company, a rapidly growing company. But prior to Quanta, he was the president of Kima T&D Consulting again, which he started. So this is his second. And before that, he was with ABB. Started the group at ABB here on the Centennial campus, which is now their main R&D headquarters in the U.S. You know, ABB is one of the biggest companies in power sector. And on the academic side, his accomplishments are more impressive. His main area of interest is power system monitoring, protection, and control. And he holds 16 patents, 112 articles, and he's a president of, he's a IEEE fellow, and he is presently chair of IEEE Technical Council, Power and Energy Society now, very important leadership roles he plays at the society. So I guess I know I cannot do enough justice presenting him, but I will just keep it short like that, if you don't mind, Damir. And please welcome him.
You should hold the applause for the end, you know.
Is it wrong?
No, just kidding. Yeah, see, that's why I'm the chair of the Technical Council. That's why I have this nice tie, Power Engineering Society tie, but I try to be having a proper color today, considering that it's a big game today. So, but color is maybe a little bit off, so sorry for that. The other thing I want to emphasize, Masoud said that, Professor Baran said that we are, growing fast, my company. And I do want to thank, actually, NC State, because we did hire quite a few students from NC State, and we actually have quite a few interns usually working with us. And these guys from NC State have been really great talent pool for us, and we've been very happy, and we are continuing and going to expand our cooperation. You will see actually there is one slide that we'll be talking a little bit about some of the cooperation that we have with NC State, my company. So, but without further ado, let me tell you what the topics are going to be today. I'll be talking about industry trends and issues in general, because for us to understand what research we need to be doing, it's good to know what's happening in the industry and where industry will be going, not necessarily maybe next year, but what's going to be happening 10 years from now. Of course, you need a crystal ball to know exactly, but at least it's good to be able to see some of the trends. And of course, what NC State has been doing in the last few years, it was really impressive with the Freedom Center, being able to lead the industry and drive where industry is heading. And that's something that I personally am always very interested in, to make sure that we help the industry moving in the right direction. We'll talk about some of the smart grid technologies. Of course, there is lots of talk about smart grid, and we'll be discussing a little bit where it is now and what's going to be happening next. The focus will be a little bit more on transmission, power system transmission. We'll be talking about some distribution issues, but transmission will be the focus. And if we have time, and depends on how the presentation goes, we can talk about some of the workforce needs for the 21st century, where we see that talent should be focusing on to be able to help the industry. Okay. And you can see this is of course the Fukushima event here, because, for example, this event changed where industry is heading quite a bit. So I hope you guys can see properly. It's a little bit skewed, but that's okay. I think we'll manage that. So
we are looking at this screen.
yeah, okay. So yeah, I'm looking at the other one. so I'll be looking at this one. So firstly, the general industry trends. It is a fact that infrastructure for the T&D system, and including generation as well, is aging. So that's a big issue, and the issue is even amplified by the aging workforce. Lots of people in the industry, they are experts at the age now, they are going to be retiring or have retired. The good news is because of all this focus on electrical power system in the last few years by the administration, by the public, and so on, more students are coming to study power, and that has been really good and has resulted in, of course, a very good trend that we see that we have more power engineers and in our industry. But this is the perfect storm, because if you don't have aging infrastructure, you can have maybe a junior person manage the grid and so on. And the other way around, if you have lots of experienced people, if your grid is aging, you can still manage that. But if you have the perfect storm, that grid is old, and you don't have experts, that's a trouble. Okay? The other element that I want to emphasize here is those 5 points here are really something that encompasses the whole grid. You know, capacity, what's been happening now because of the economy going down. There was not much capacity development in the industry. Utilities have been reducing their spending because they don't build substations, they don't build distribution networks as in the past, because economy has not been growing those type of, didn't need that investment. However, reliability has been a major focus, because these days we really need uninterruptible power. With your computers, you know what happens with the TVs and all the stuff. So let's not go there. I think it's well known. I'm just going to pick up a couple of things here. One big issue is now security. Cybersecurity has been a huge issue. There are all these concerns now, and there is, I don't know how familiar you are with the Federal Energy Regulatory Commission, FERC, and NERC, and so on. They've been putting tremendous pressure now to address the security issues. All the things that I'm talking about, please start thinking from the research perspective. How would, let's say, NC State as a university be able to help address some of those needs of the society? This is now the big issue, natural gas, with shale oil and all this. And you can say, what does shale oil has to do with electrical power systems? It's a huge changer. I can tell you now, with renewable energy, there is going to be less investment in renewable energy because of this. So now when we're talking about research going forward, what we need to do, it's becoming less important, because natural gas will define roles of other resources. We have the issues here with regulation now. Of course, we still have renewables to achieve social and political goals. At the end of the day, still solar and wind and so on has this environmental impact that is important. And it's going to continue to be important. But it's the holistic view. If you look into this, this is the keyword, holistic. You have to look at all these things together. But this is the fact now. The big issue now is retirement of existing fossil and nuclear plants. In Germany now and Japan, they basically put moratorium on nuclear. So they're not going to do it. Okay? So now what's the alternative? And again, with natural gas, now there are lots of gas-fired plants being built as we speak. And at the same time, these other plants, fossil and nuclear, are getting retired. Especially fossil in like Northeast, in California and all this is getting retired. This is also related to T&D system. Because, and I'll show you one slide, if you have a generation that is far from the load, you have to do something about it. Building transmission lines and all this. I can't underestimate the value of importance of electrical vehicles. I'm a firm believer they are here to stay. We can talk about there were electrical vehicles 30 years ago, whatever. But now it's happening. finally, the manufacturers have started investing and putting products on the market. So that's what's going to happen. We'll talk a little bit about the impact on the grid because this is of interest to us. So in general, the system that we have now needs reinforcement, needs integrated system planning and automation because system is very complex. Just think about how the system is now. Wind, solar, intermittency, and lots of different sources, need for efficiency. So we end up with complex grid structure requires smart grid solutions. So to me, that's the simplest definition of smart grid is system is complex. We need to manage it smarter than we do now. And that's what smart grid is all about. Another aspects here. So renewable resources that require infrastructure. You can look at the map, and I didn't have enough space, the slides to put all these things in. But if you look at the map where the solar and wind is, it's not where the load is. So that's the big issue. So what we see congestion, difficult to schedule outages. I'm showing this one slide here that is actually you can do work on the system live. You can do maintenance on the transmission line by doing like this. You have a robotic arm. You take the robotic arm, and you take the conductors, and then you can go and work on your tower. At the same time, the power is still flowing through the conductors. So you don't interrupt the line. Because the problem with congestion is system gets congested. It's like the traffic. If you have too many cars, you get congested. Okay? The same thing is with power system. You can get congested if you don't have enough lines of traffic or if you don't have enough transmission lines. So if you take one, what happens? Then the other gets overloaded, and then you get a blackout. And we'll talk a little bit about blackouts here in this presentation as well. That's why I have so-called system integrity protection schemes. Focus on planning operations, modeling. And this is a very important thing. And we have here in this room, we have some of the industry experts in modeling. And I don't want to call all the professors' names now. I'm afraid I'll forget somebody. But NC State has been leading the industry in area like system modeling and so on. Next generation EMS and SCADA. We'll talk about so-called phasor measurement units. I have a slide on this. And you go further, very important thing with Freedom Lab, power electronics. Extremely important technology, and NC State, again, Freedom Lab is the leader in the industry related to power electronics. And we cannot underestimate impacts of fax devices and full current limiting devices and all the other things. Okay. With so-called distribution smart grid, there is lots of talking about AMI, metering infrastructure, and so on. Has been actually a huge issue in a way, because it's becoming now clear that some of these projects, some of these huge investments that were made, do they really bring the value? If you look into automated meter reading, that's all fine, but you don't really have to have all this infrastructure to do automated meter reading. So what's the value? Demand response. Okay, are we doing demand response? The big issue now, guys, is the conservation voltage reduction. This is basically to reduce the voltage to minimize the losses and so on. And I know Professor Baran and actually I worked on this, when was it, about 20 years ago? So now it's becoming a very, very hot topic. And that's how you justify all these smart grid investments, by having more applications added to what was been there. We talked about the aging workforce. So smart grid phases. It started with lots of hoopla, lots of talking and misunderstanding. It used to be this saying that as many people you ask, that many answers you'll get for the smart grid is, and all this stuff. Okay. But the bottom line was that in phase one, the focus was to really develop understanding what the smart grid is. It started with smart grids AMI. So probably 90% of the people originally thought that's the smart grid. And you say, how can grid be smart if you're only focusing on one part of the grid? That's stupid grid. That's not smart grid. So you really need to look into the whole distribution system. You need to look into your customers. You need to look into transmission. So smart grid without smart transmission makes no sense. Without smart generation. So it has been realized If I may say that, hopefully I helped a little bit, just a tad, to have this understanding properly communicated to the industry. That is the holistic approach addressing operational, regulatory, commercial drivers, all technical domains to be able to really get the benefits. And you can see here on the right there is a slide that talks about some of the important elements of smart grid. Okay? But let me go further. Phase 2. We are now in the middle of phase 2. U.S. government has invested about close to $6 billion into so-called smart grid projects. This was all matched by whoever got the project had to match by 50%. So we double it. Then utility commissions, the local governments of the states, they also supported this. So the investment was made about $20 billion. That's the rough estimate. So this $20 billion would have to be spent in 3 years. So it started last year. This year is when it's happening, and it should finish basically first quarter or second quarter next year. Why is it like this? Think about the reason why 3 years and why it's ending in the end of 2012, beginning of 2013. Who can guess? Presidential politics, of course, because Obama needs to show that the programs that he started under his administration are generating results. Jobs, making system more efficient, and all this. So that's basically, we are in the middle of this phase. What is really happening now with this phase is that we are evaluating these benefits and comparing them with expectations. There was, I can tell you a couple of stories. One was Boulder, Colorado, when they had this smart city. There was all excitement, all the benefits. So when they started digging and putting some cables, you know, and so on, they figure out why the city is called Boulder. So of course it cost much more money than they originally estimated because they didn't really factor it in properly. So suddenly it was all over the, you know, you can get on these internet sites, Boulder, Colorado, and you don't hear about Boulder, Colorado anymore. That's it. Because there was no business case. Okay? So we are getting there now to identify what are the real benefits and comparing them with what's been really realized. In PG&E, they had a major issue. They put meters, and then suddenly the people that were having those meters, their bill went up. So they said, this is horrible. We want to cut this. We don't want more meters. So they started blaming meters. The issue was that what happened was that also pricing structure has changed. So it was not really the meters, but it was the pricing structure. And also pricing structure included that you need to, demand response. So if you use electricity from 4 to 7, then you pay more. Okay, and people didn't really maybe pay attention, so suddenly they are paying more. And there is all backlash. They want to actually get out of Pacific Gas and Electric. They want to join the municipals. They don't want to do it. They don't have anything to do with smart grid. You see the complexity of all this, what we are talking about. Okay? But anyway, success of this development project will help actually define what we are going to do next. So these projects are very important, and I want to make it very, very clear on this because I gave a talk on this at the Smart Grid in Washington. And then the IEEE guy took my talk and then wrote an article and put it on the web. And I look, what he wrote is not really what I said. So I have to be very careful what I'm saying. I'm just saying there are lots of benefits coming out of smart grid investments. Okay, it's just the issue is that we now are at the stage to identify what they really are. That's all of what I'm trying to say here. Phase 3 will be moving. 2013 is normal course of business. I can tell you that 2013 nobody will talk about smart grid anymore, or 2014. That's it. So let's just focus now on what's going to be happening going forward.
That's kind of scary, though.
Actually, it is. Especially if administration changes, guys. There's going to be a major difference in approaching so that is going to be different. Okay, and that's my talk is about. Let's try to see what's going to happen and position us better to move forward. So anyway, smart grid standards activities. I do want to emphasize that it was properly recognized by the industry, by Department of Energy. that if you have all these new technologies, AMI, distribution automation, substation automation, demand response and all, you have all these products. If they're not interoperable, you create lots of problems. So the understanding was that you really need to work on standards. The key thing is that standards by itself will not assure interoperability. So let's not fool ourselves, but they are a very important step in assuring interoperability. And developing standards, what needs to be done, actually it's in a way a research topic, going forward. So this is something that is worth, I think, exploring more in our industry in general. So again, I'm not going to go into the details. That National Institute of Standards has established smart grid interoperability panel that is working, and they released the so-called Roadmap 2.0. I'm pleased to say that actually myself and my guys actually worked on that roadmap. They were actually helping develop some of those standards. Okay, let's move on. This is the example of joint effort with North Carolina State University and quantum technology. I'm very proud that we have that lab together that has been successful. Professor Subhashish is not here, I guess. I don't see him, to give him some credit for, and of course Aranya and the other, Professor Aranya and the other guys here that have been really providing a major contribution to developing this lab. But to describe a little bit more on what we are trying to achieve here, we have so-called real-time digital simulator, the closed-loop simulator that you can actually simulate the power grid in real time. And let's not go further. And actually, there are a number of universities and a number of utilities that have that simulator. So why are we different? Why are we better? Because we are tying it now to all this work in power electronics, into renewable energy, developing models, and having really the approach tying the applications to how to use the simulator. I can tell you, simulator was used for one very important initiative in the industry. Dominion, that serves Pentagon, got utility Dominion, was asked, they say there is the problem with so-called aurora effect. Aurora effect means that if you can penetrate some of the control devices and protection, you can trip the generator. So you do the opening and closing of the breaker. You open and close the breaker constantly, you create instability in the system, and you trip the generator. Okay? And they did some tests. I think it was PNNL did tests, Pacific Northwest National Lab, and so on. So they did the tests, and they showed that's a possibility. Okay? I personally believe there are much easier ways, actually, to destroy the system than, because you have to have tremendous knowledge of the system. You have to be able to get into the devices, all these things, but maybe that's just my personal opinion. In any case, so they were told by FERC that they need to install this type of device. And a couple of vendors have the device. And they said, we are scared, because we install the device, and the device starts tripping, and we are actually disconnecting Pentagon. So they asked us to help them evaluate. And what we did, again, using our joint lab, we basically modeled those events with RTDS, and we're the first group in the industry that actually tested what it really does. And actually, we did find out that if these devices are not properly set, coordinated, that they will trip. They will cause more harm than they will do good. And then after this, NERC and FERC actually accepted some of the results, and they've been adjusting the regulation based on the work done in our lab here. So again, that's very good. So I'm really looking forward to expanding the cooperation. We'll be doing some of these interoperability standards jointly. With Professor Anya, we'll be doing some PMU stuff and 61850 and all these things that we plan, and we'll be using students, of course, you guys, to work with us and make things better for the whole industry. Okay? To make sure that I'm managing my time here. Impact of plug-in electrical vehicles. There is lots of discussions on plug-in electrical vehicles and the benefits and charging and so on. What I'm going to focus on is impact on the power grid. And we have done some analysis that shows that actually there is a significant impact on the power grid especially if it's uncontrolled charging. But even with the controlled charging, there is a major impact. It depends, of course, on the level of penetration. And what that impact is, let's assume you have a transformer. And usually you say if you have electrical vehicles, you can now do this charging when there is off-peak. That's the big benefit. You say, okay, you come your home and you start charging at midnight. Nobody's driving, nobody's using electricity, so you can actually charge. What's the issue here? If you have a transformer, when manufacturers design the transformers to cool off. So if you would have constant load, it's very bad for the transformer, because transformer was designed to be at certain level and then cools off, and then the current goes up. I mean the heating and all this stuff. So that's the bottom line. And you can see the study here that shows how some of the transformers can be overloaded if it's not carefully managed as well. Okay. I'm not going to spend too much time on this, but I've been big on this holistic approach. This is impact of photovoltaic and electrical vehicles together. So it shows you this slide here. I'll try to use this new technology for the first time. So let's see. If this is if we have the base case, no PV, no EV, I think we are here. If we have now with PVs and EVs, actually no, sorry, this is the one. If we add PVs, we go down, because PVs, feed into as a microgrid to the system, so you actually have less load here on the feeder that feeds from the system. But now, if you have uncontrolled EVs, then you're getting all the way here. Now, if you have controlled EVs, you're getting to the red. And again, I'm not going to now go into the details explaining what it really means and so on. Just to give you a flavor of what type of work and studies and analysis would need to be done to understand what the impact really is. Okay? We talked about shaping the future with smart transmission. This is a typical example. This is Midwest, lots of wind. This is the area with lots of wind. But how many big cities we have in the Midwest? North Dakota, South Dakota, and Minnesota, and so on. I mean, we have Minneapolis. We have actually Chicago is there as well. But the bottom line is, where the wind is, you don't necessarily have a high load. So going all the way from the west to the Midwest, there is this whole area here, this area, and here, that you don't really, they have lots of wind, but you don't have much load. Because your load is in New York and Philadelphia and Washington and so on. So the idea is now how to really bring that wind to the load centers. And that was the analysis that was done. And you can see the numbers here, just to give you a little bit of a perspective. So there were three alternatives here. And three alternatives were, the first one was, let's focus on 345 kV mile lines and some 765 kV and some HVDC. When it says under sea, it means it's under lake, because of course there is no sea here. Okay. So the other alternative was focusing more on 765 kV. Okay. So B and BA, alternative 5 and 5A are more with 765. Again, why my story here is that, firstly, what's happening in industry, where the investment is going, and to looking into what type of technologies we need to be developing to be able to serve the system as it's growing. So the system, look at the investment here, $23.8 billion US dollars, $24 billion US dollars. I can tell you that after this study, they started building some of those transmission lines. Okay. San Diego blackout. I don't know, have you heard about the blackout in San Diego? It happened about, I don't know, 3-4 months ago. Okay. And blackouts usually happen as the sequence of low probability events. What it really means that why don't we have blackouts very often? Because we do manage the system, but statistically, mathematically, you will at some point in time, some of these events will happen at the same time. And if you are not able to respond to this, then you get into the blackout. Okay? And let's see briefly how it happens. So firstly, I actually have that story. I do need to tell that story. When the blackout 2003, August 14th, there was the huge blackout. 57 people were affected and all this. I remember I got a call from the Japanese radio station, J-Wave. And they wanted to interview me, and they claimed there is like 5 million people are listening. That's the most listened radio station and so on. And when I was interviewed, I actually tried to be a little bit probably too technical, because I tried to explain there is never one thing. There is not a single thing that really causes the blackout. Blackout may start with one event, but then some other things have to happen in parallel that are not predicted. There are low probability events and so on, and then the problem happens. And now imagine when you try to explain, and they are translating me to Japanese, so it didn't really work too well, but I learned that, at that time they said that there were 3 T's that caused the blackout. And if I said that, that would have been actually 3 T's were trees, tools, and training. So we didn't do in the US, we didn't do in North America, trees, tools, and training. But I can tell you I disagreed with this technically. As a research technical guy, I said that's not true. Even if you handle trees, training, and all this, we still did not, shouldn't have allowed blackout to spread out to that large area. Because that's the problem. It's not a problem. Outages will always happen. We cannot, unless we invest, even if we invest billions of dollars, and we'll still have outages. But you need to be able to prevent them. And my next topic will be actually how to prevent outages. But that's why I wanted to start with this example. So outage started at human error. One person was doing maintenance on a series capacitor and tripped the protection, and it disconnected the line. So transmission line gets disconnected. Of course, line gets disconnected. We talked about congestion. So then the other lines get a little bit more load. Very, very simple. But then what happened? Generation in Mexico tripped. And it was unrelated. It has nothing to do with that series capacitor being tripped. So, but that's what happens in life. You know, they disconnected this generation. As soon, so there is no generation coming here. So suddenly you load this path, so-called path 44. So there is no generation here. There is no generation there. And everything comes here. And this is San Diego here, you know, big city. So you load this, and what happens? So I'll go actually to the next slide. And I'll just show you so 500 trips, generation tripped in Mexico. Then you have transformer banks that were getting overloaded. They trip. Then once you start overloading the system, then things start going the wrong way. Because all the other lines get overloaded. They trip due to protection, or if they sag, people say, okay, that's the problem in trees. But let's say there are no trees at all. If you don't do anything, the line will go down, will hit the ground. And it's going to be the same thing. So again, if you want to be really technical, then you really get into the root cause of the issues. But anyway, blackout occurred, it took about 11 minutes, and the system was restored in 1 day. I'm now showing 2 other blackouts here. That was the one in 2003. And again, I'm not going to go into the details here now, but my point is they're actually very similar. So are we learning from our mistakes? Have we analyzed it enough? And then when people are designing the system going forward, do they take advantage of the knowledge that we gained in the past? Okay. Again, I can talk about this for the next couple of hours, so I'll better stop here. This is also what has changed in the system. I think this is actually a very important slide. Because I remember this original slide about 15 years ago. This original slide was developed 15 years ago. But the original slide, what it had? Original slide and I should have shown this, didn't have this, didn't have this, didn't have this, and didn't have this. What it means? If it's a densely meshed power system, it's like northeast, all dense, lots of load. What you have problems with overloads, overload in the transmission lines. If the system is lightly meshed, what you have? You have problems with transient stability. Okay, that was the 15, 20 years ago. That was, or maybe more, 20 years ago. That was how system was operating. What happened in last 15 years? System has changed tremendously because of all these things that we talked about. So now you have all those problems in all the systems. Voltage stability, and I'm a little bit older guy, so I can tell you in the 70s, you see how old I am, the voltage stability did not exist. Nobody knew that voltage stability is an issue. Okay? Now everybody talks about voltage stability. And if you look now, all the blackouts, they have some element of voltage stability involved. Okay? So that's why I put 2 stars here. It's still, in the lightly meshed transmission network, you still have more transient stability problems. Still in densely meshed network, you may have a little bit more overload problems, but it's all happening. And you cannot distinguish. You cannot say what caused the blackout or which one of these events. Very often, all these happen at the same time. It's very difficult to actually distinguish between transient stability and voltage stability if you think carefully. Am I right, Professor Aranya?
Well, for one you have to look at the voltage, for the other one you have to look at the angle.
Good, see? But the problem is that in the system you have both angle and voltage problems. See, that's the bottom line. By the way, guys, please, I'm sorry, I should have mentioned this at the beginning. Please interrupt me if you have any questions. I would like to make it more informal. So please feel free, okay? So let's look at the time scale. This is also actually a very old slide that I've been using for quite a few years. We have fast short circuit faults, fast dynamic response, protection fax devices. We have SCADA, EMS, system operation, long-term stability, market transactions. Now, the middle area, again, 20, 25 years ago, was not really covered. Now, thanks to the research and understanding of the phenomenon and all this, lots of effort has been put here. Lots of effort. Actually, again, sorry, calling again, Professor Aranya is organizing a workshop in Taiwan that is exactly on wide area monitoring, professional and control. Okay? So very important topic. But you see the time scale and time scale for modeling. So now, as students, when you're doing your work and so on, you need to look into models that you are developing. What time frames this model need to be covering? Is it long-term stability, mid-term stability, short-term stability, transient? What type of models you need to be using. Okay. So I'll talk more about this. So synchronized phasor measurement technology. Technology that are precise grid measurements using GPS signals. It's actually very interesting that nowadays, if you drive in a cab, most of the cab drivers will have a GPS. Am I right? I can tell you in our substations, we don't have, in substations we don't have GPS. It's kind of silly. You can have it in a cab, but we all talk about how important the T&D system is and substations and all this, and then we don't put GPS signal into this. So the bottom line is that I always say this is not a rocket science. It's actually a relatively simple technology. What you do, you get your GPS signal and you synchronize the measurements across the grid. And synchronization is done in a matter of microseconds. That's actually the standard. The synchronization is 1 microsecond. And you have ability to monitor 30 to 120 observations per second. So think about EMS SCADA systems that sometimes do refreshing every minute or every 2. You now suddenly have a system that can do a lot more. Okay? So this type of technology enables indication of grid stress and maintain reliability. So if you have ability to see what's happening in the system, and there was actually one good comparison. Think about a hurricane coming. And we knew, for example, the hurricane that hit New Orleans. The hurricane, we knew the speed, we know all these things, and still the damage that it caused. Very often in power system, we don't know some of these things that are happening. And these type of devices help us to have this visibility and make sure that we can understand what's happening in the system. Okay? So some of the benefits of this technology, analyzing the data, visualizing, that's key. And we already have significant benefits achieved. We have system reliability prevention using these devices. That's huge societal benefit. Imagine preventing one blackout. So when we talk about the investment, and that's why DOE, and I'll talk about it in the next slide, invested so much money in this. Because preventing one blackout can save how many billions of dollars? Okay? System operation planning, modeling, that is very important. Dynamic models. We talked about these time frames and models and so on. PMUs can give you a chance to better model the system and test your models, understand our models correct or not. Okay. Market operation, congestion management. How a system is managed now, it's a worst case scenario. I showed you some of these events just recently. Overloads, frequency instability, voltage instability, transient angle instability, and small signal stability. Okay. These events and system is designed for the worst case of all, of each of those. Okay. So if you know that you may get voltage instability or overload, you will design the system with the worst contingency. But the worst contingency may not be what's happening now in the grid. So why are you now allowing power to flow through the line based on the worst case? Don't you want to know what's exactly happening? It's the same with like dynamic line ratings. Are you guys familiar with dynamic line ratings? Because again, you rate your transmission line for the worst case versus dynamically. Okay, so the bottom line here is that the tremendous cost can be saved because from the if you can push more power, you don't have to maybe build new generation because you can push more power to the line, or don't have to build new line, whatever the business case is. Okay. Okay. To explain some of the talk about some of the projects, and you can see all this investment that has been made. This is the latest from NASP. I'm actually on the leadership committee of NASP. And see how this map about, I don't know, 7, 8 years ago, they were like 10 times less.
Very sparse.
Very sparse, exactly. So this is the investment that was made, and you can see all around the country. I mean, again, I'm happy to say that that my company is involved in 70% of all those projects. So, and this is to show us. And again, let's take from the research perspective. What's happening now? You have a number of PMUs that have been now in those three-year development projects. And here is the applications. So you have conservative is small number of PMUs, basic applications. Or aggressive is you have really high-end applications and lots of PMUs. And applications are just doing monitoring. That's it. You monitor and you analyze in the outside of control room. You visualize in the control room. That's the next level. The third level is you have some real-time applications. You do something. You trip the line. You switch shunt capacitor off or on or whatever. The big bang is you have full-time closed-loop control, protection, operation, and other stuff. So what's happening? I didn't want to, of course, put the names of the individual utilities or ISOs, but you can see it's actually very easy to see. These are all ISOs, independent system operators, because what they focus on having as many PMUs as possible, but applications are not too high. Some of the utilities are focusing more on applications, but they don't have that many PMUs. But as you can see, nobody is really here. So there is lots of research to be done in that space. Lots of work yet to be done to move forward and to get where we want to be. Okay. Okay. I'll go fast through this just to tell you how the technology has been developing through the years. First device, we see now all the vendors have the devices. But there's lots of work still to be done. There is lots of work in distribution now, by the way. I actually may be wrong here, because I said in distribution 2018. I see now more and more people are using it in distribution. Okay. I'm going to talk a little bit about voltage instability, go a little bit drill into the research technology area here. So voltage instability, and I'll do a very simple approach. This is famous PV curve. That's how voltage stability is usually described. So what you have here, if you have inability to maintain a voltage so that power and voltage are controllable, you are voltage unstable. What it means, if you get beyond this knee of the curve, you are getting into the instability region. And then you get into the outage. You can get into the blackout. Okay? So if this is the pre-contingency case, this is the post-contingency because it happens, system is stressed, but then you get a trip of the line. We talked about this, line trips, and then system gets more overloaded. Then voltage goes down. Then motors start stalling. If motors start stalling, they draw more reactive power, and you go into the old, again, I don't think we have time for go into the very technical details here. So, but you have this, this margin if your peak power is this. If now load increases, and you have 108 of percent peak in 3 years, your margin goes down. And that's what's happening has been happening in the systems. People are getting more, systems are getting more stressed, so we have more problems with issues like voltage stability. But how to measure this? That's the big thing. How do we know the system is unstable? And you look at the real-life PV curve. It's pretty messy, isn't it? How do you decide now? You can say it looks nice. If you look at this picture, oh, I'm here, I know I'm voltage unstable. But in real life, things change. Lines trip, close, open, whatever. You don't know. Where are you now on your PV curve? So it's a little bit, fooling around if you think that just by looking at the PV curve we can detect if system is unstable. That's not really that easy to do. Okay? So understanding what's happening. Okay? So in general, voltage stability issues, I want to emphasize long-term instability that happens in a matter of, we talk about minute and beyond. Low proportion of motors in local load. We have system instability that is a short term. When you have motors in local load, it happens much faster. We have the situation here, so-called fault-induced delayed voltage recovery. That's a new phenomenon. It was discovered a few years ago. That wasn't really, I can tell you, 10 years ago, nobody talked about fault-induced delayed voltage recovery. Now it's a big thing, especially in the South, Southern Company, and so on. What happens is you have a fault, and voltages get depressed due to the fault. And as voltage goes down, again, motors start stalling, but they don't trip. So they draw reactive power. Once the motors trip, because they may trip on some thermal protection, whatever, suddenly you have overshoot. So, and you know what happens here? See, that's the tricky thing. You get low voltage, and you say, oh, let me put my shunt capacitors, include them immediately. Let's turn them on. So you turn on all these shunt capacitors to raise your voltage. Motors trip, and suddenly all your shunt capacitors are on, and you get to overshoot. You get into a bigger trouble. So those are the things that we are looking into. So I wanted to show you one simple example of research project that was done with Southern California Edison and BPA on how to so-called voltage instability predictor. It's based really on actually very simple theory that your maximum power transfer will be when if you look at a system in just a very simple system here. This is the bus, this is the load, Z Thevenin and the source. If Z apparent is equal to Z Thevenin, that's the point of collapse. That's actually the knee of the PV curve. Okay. The idea originally has been that we try to use the voltage as indicator, but I'll show you why voltage is not such a great indicator. So you have methodology that can able to track. So you track your Z Thevenin, and you test your Z load, and you're actually measuring the margin. And as you can see, as you're going here, you can exactly know how close you are to voltage instability point. And then you can then detect it and say, I need to do something about it and take some control actions, whatever the control actions are. Okay? And it's much faster than doing it by EMS SCADA systems. You use actually PMUs for this, so it's more accurate. So I'll show you I'll just mention this as a simple example. If this is the voltage instability region is green in the RX diagram, this is what undervoltage signal really does. So you can have point 1 when voltage is actually getting low and you trip but it's still not unstable. You're looking into the situation as number 2 where voltage is actually not too low, but you have all these shunt capacitors that keep the voltage artificially high. So what happens is then, because you are really close to the knee, then suddenly you have precipitous voltage drop because you don't have dynamic sources of reactive power. And because you don't have that, then you trip immediately, or you get into the voltage instability. And your regular undervoltage relay will not tell you that. Okay? So the approach is here really to calculate the model-free approach, calculate the margins, reactive power margins for some very complex situations. As you can see, load center, there are a number of PMUs. And I can talk about all the details of the derivations and all the equations and so on, but I don't think we have time for that. But well, I want to show you the let me just move here. Some of the results on the concrete system. Even if voltage is close to nominal, it's able to detect that this is unstable. Actually, for this Fidver case, remember we talked about, voltage can be very low, can be 0.7, and it tells you, no, it's not voltage instability yet. So it can really help you detect the instability. And this is how it does the calculation. And again, there are very detailed equations all behind this and calculations and so on that show these are stability lines before boundaries before line tripping. This is the stability after line tripping, and these are the operating points. And you can see what the margin is. You can translate this margin very easily because you can always transfer from the impedance diagram to the power diagram and so on. And that's what you see. You see how in time, you see how margins drop. And you know what is this? This is the switching of the capacitors. Capacitor switched here, capacitor switched here. Okay? And then you go down and suddenly you see you are in trouble. So you still have some time to do something. Okay? And this is really good. Operators love that. Operators just love it because that's what tells them. Right? You don't have reactive power, do something. Okay? Okay. And as any research project, and we had a good discussion today over lunch on how long does it take for a research project to become implemented in the field. So we've done this research for a couple of years. Now we have good results, seems to be working well. Now to implement. It's still what these guys are saying from Southern California, this and BPA. We'll now install that system, and this is the visualization. We'll install that system, we'll let it sit now for a few months. Because that's fine, all the studies, all the data show, and we actually use the real-time data, by the way, with PMUs. So real-time data have been used, but still, you want to sit there in the control room, but without doing any actions, just to see that it works. So it's going to take 1 year or more to really implement in the real world. But that's always with research. We have to live with that. So that's how it is. So anyway, I don't know how much time. I don't think I have much time.
3-4 minutes.
So I'm actually close to the end now. I did want to emphasize this point of we are doing good as electrical power engineers. It's great. Guys, companies are hiring electrical power engineers. I'm hiring on a regular basis. I actually always have to compete with other companies for good resources. Fortunately, you always get good talent and good resources from professors from NC State. So again, I cannot thank them more. But what is really important here? Firstly, again, it's going well. Universities are putting focus, Freedom Center and all this. This is exciting. But skills required are broad and not traditional. It has changed. It has tremendously changed. I know you guys. You know, when I was studying, you know, we didn't have computers at that time when I was studying. So think about how many more classes you need to take as undergrad. And that's really difficult, because once you graduate, you still don't have really knowledge about power system, because you have to take all the other courses. So that's the really difficult problem sometimes to resolve. Willingness to accept some of the smart grid technologies and so on. The future is with you guys. You will be the ones that really be making it happen. So, but this is important slide for me, because if you look what the technologies are required, telecommunications, cybersecurity, computers, if you're in power, this is all what you really at least need to touch somehow. I mean, I have to talk all the time about cybersecurity. I'm really not a communication. I have no clue. Okay? But constantly, even these standards, I constantly need to, at least I'm chairing, that's in a working group. So I need to have people that understand communications for me to actually get the job done. So telecommunications, cybersecurity, of course, computers. Human-computer interaction. I mean, this is the important thing. We talked about visualization. You saw all these graphs. You know, we as engineers, sometimes we would be very technical, you know, and operators sometimes want simple things. So you really need to have somebody that understands how you do the human-computer interaction to be able to do proper displays. We have actually a project now where we use resources from one other university where we actually have HCI guys. They have no clue about power systems. Okay? Control theory, system engineering, batteries. We talked about electrical vehicles, batteries, storage, all these things, you know. So, but it's very exciting, okay? But we still need to keep traditional. I'm actually teaching course here, or not teaching, I'm sorry, I couldn't say that. I'm helping Professor Baran a little bit to teach a course. And I'm protective relaying guy, that's my deep technical area. So I used to teach actually a little bit more in the past, and maybe in the future I'll be helping more if needed. So, but protective relaying course, there are no people now in that area. There's a tremendous need. AP sent a note. If you go on the web, you will see AP. 20 engineers in protection to hire immediately. Very high salary, actually. I'm worried maybe some of my guys will actually leave the company to go to... I'm just kidding, but that the bottom line is that they need 20 engineers. Now, just one company. Yeah. Protective relaying, how many protective relaying engineers we know we really have? But you see, NC State, again, with the vision of Professor Baran, has that course. And you go to that course, you can go and apply AP. I had the course in protective relaying, I know this stuff, and you get a job. That's it, as simple as that. So guys, just let's remember this also, what are some of the traditional things are needed. Okay? So actually that's about it. I want to emphasize long-term growth and earning potential is important. And you guys tell me if I'm right on this. I wrote this thinking about that's what you want. So read and tell me, have I missed the boat? I believe you want to have long-term growth and earning potential, not short-term. You want to really, 10, 15 years from now, you want to say, I'm going to have a steady job, well-paid, and I'll be able to grow. Okay? You want to learn skills in the growing game-changing technologies. We need to excite generation to create smart, innovative applications they will want to work on. Something exciting. Remember how it was in the past. What's power systems? It's the transformers, transmission lines, old boring technologies. It's not the case at all. Freedom Center. Think about all the exciting things that you guys are working on here. It's amazing. It's great. And that's what we see here. Making a difference. Personally, I'm really big on making a difference. When you go through your life, you say, you want to look back and say, I made a difference. That's what counts at the end. Okay? It's fine, you make money and all this. This is all good. But at the end of the day, making a difference, I believe, is more important than making huge amounts of money. But then maybe that's just me. Okay? Okay, and I want to emphasize aging workforce and lost expertise is not being replaced at required speed due to lack of past investments. Trained and sophisticated workforce is needed. Do you guys agree with me? Okay. And this is the last one, last slide. Actually, no, it's not the last one before last. But system quite change. 90s to 60s, it was generator to meter. It was regional, local regional, mostly radio. Today, we have market trading. And of course, because of market trading, we got into some of those problems. Because system was not designed for market trading. System was designed regionally. And they said, OK, let's connect the system to improve reliability. So reliability got improved. But then they said, OK, now we can do market trading. We can sell power from a very far area to another area. Once you start selling power, you stress your system. Voltage stability. You cannot solve the voltage stability. You have to have it locally. Voltage stability is a local phenomenon. Okay? So system has changed. What's going to happen next? What's the role of the system? Is it microgrid? Maybe microgrid is the solution. Okay? So there are lots of, we don't have time to go through this. I just wanted to kind of give this to you to a little bit think. What do you think the system would be in the future? But what we do now, in 2015, will define what's going to happen in 2040. We'll make the difference, because now is the time to make the difference. Okay? And again, this is the last slide. I love this slide, actually. So again, what future brings?
Well, thank you.
Do we have any time for questions? Or? Yes.
And I like how you stress sort of that you're very right in saying the young generation is excited to sort of embrace the smart technologies and stuff like that. But I think the reality is that the capitalist market system isn't quite so ready to jump onto it just because of high capital and things like that. So, and I know the growing trend in Washington is to sort of drill or frack our way out of our energy problems. So how do you think we can interact with that market system to allow these kind of changes without going broke?
Yeah. And that's an excellent point here. I'll tell you when Obama's delegation, Obama was actually here, visited NC State, I believe, and his team with Immelt from GE. President is on his leading his task force. He was actually at NC State here, and we were at the meeting. These guys were kind enough to invite me to be at that meeting. And what was interesting, there were all these leaders in the industry. And these guys were asking from Obama administration, what do we need to do to make things happen? And they said, just give us a clear policy. All this fuzzy stuff, it really makes it very difficult to decide what we want to do. Now, coming back to your point on how to change this. But when I said young generation, is the young generation becoming leaders in the industry? So you will, through the years, become leader in the industry. And that's how you change that. Sometimes it takes a generation to change the things. See, that's really the point. It's not when you come to let's say you start working for the utility. And utilities, I mentioned this, actually they still have so-called electromechanical relays. There are almost 50% of substations have electromechanical relays. And it's amazing. And we talk about smart grid, we talk about all this. And we even haven't done that yet. But as you guys are coming to become leaders, then you will be changing this. So it will take a little bit more time. I agree with you. Okay? Have I answered your question? Or? Okay. Any technical questions? Yes.
Actually, it's related to power generation more than smart grid. I think it's the main issue is that there's a huge demand on the power grid, so this is what makes it unstable. So most of the money is invested in new technologies like nuclear fusion reactor. They invest billions right now in this. So what do you think about it? So do you think it's more important to meet the demands more than have smart grid?
This is always, I'm a big proponent, of course, of smart grid, and but smart grid is really using the technology and innovations to manage the grid better. Okay, so when you asked where to invest, where is better to invest, you can have the smartest grid in the world, all the telecommunications, all the monitoring, everything. if your transformer is old and it's not replaced, doesn't help you. So you can get the signal that, you know, you get a signal, transformer is old and so on, but you have to still replace it. So smart grid will not help you. The same thing is with some of these investments. It all ties together. You know, you cannot treat one without the other. And where to invest, of course, as you say, there was this huge investments into reactors and so on that now may actually be useless because there is the backlash against nuclear. And I'm personally, I'm not sure that's the right approach. And again, I'll give you my personal opinion that, of course, there are issues with nuclear and all the stuff. But at the same time, it is clean energy, and it just has to be managed properly. So we have to be, again, looking holistically into the system. So, yeah. Yes.
Could you tell us very briefly what a microgrid means?
Yeah. A microgrid is actually if you are handling the local grid as self-sustainable. So instead of what we have now in the grid, and that's this picture here. I'm glad you asked the question here. We have the grid that you have from the you have the generation, then you have the transmission system, and you have distribution, and then you get to the load. And now we say, let's say we have wind, and now we are going from we talked about Midwest, wind traveling across the whole country to get to the load. Now you say, maybe we should do it the other way around. We should create the grids that are self-sustainable. How they can be self-sustainable? Let's say if you're in the area where you have lots of solar. You have your solar plants feeding the local grid. Wind. That's why storage becomes important. Again, I didn't have, of course, enough time to talk about all the things in detail. But storage there's huge investment now in storage. Because that's how you can actually handle microgrids if you have storage devices that can manage it. So any comments on microgrid? I know they're actually better experts than I am on microgrid here in this room. So I feel like I shouldn't be talking about it, but
It's a pretty good
visualization
of microgrid.
Okay.
Comparing the U.S. and I'm sorry, somebody else. Yeah. Us and the Europeans and the Asian countries, are we ahead of them in smart grid technology implementation, or they are? I mean, I didn't see any slide.
So that's always good to have these questions, because that was one thing that I was planning to talk about and I didn't. So, firstly, to the first point that was made, it's at the end of the day about the investment. What happened in the U.S. was that government decided that we will invest in smart grid. They put all this money, that's what happened. Like with these PMUs, we can say whatever we want, but they would not have happened like this. It would take at least 10 years more or whatever, but the government invested money. Now, how it relates to your question? Because what's happening now, U.S. actually got into the lead in that area. But the others are now following on this. Europe is actually behind on smart grid. When we talk about smart grid, I mean, they may be ahead in wind. They may be ahead in storage. I think especially in wind, they actually put lots of effort in wind, especially offshore wind now. Of course, it's much easier to do offshore wind in Denmark when the sea is very shallow versus of the, let's say, west coast. It's very deep, so it costs lots of money. So, but to answer your question, again, U.S. has been ahead. We see tremendous now initiatives in Asia and Latin America. Asia is India and China. People claim actually that China is ahead related to phasor measurements. I actually disagree with that. They may have actually more devices even, but I don't think they have really implemented and applied them any more than we've done in the States. But again, that's my opinion. But I know that India, China, Taiwan, Middle East, Australia, Latin American countries, Colombia, Brazil, they are putting now major focus on smart grid. But I think they are a little bit behind us.
some of your previous slides, you talked about the local voltage stability indicator, right? Based on which you compare Thevenin equivalent impedance and load impedance to identify the closeness to loadability limit. Right. My question is that do you estimate Thevenin equivalent impedance only using phasor measurement unit data?
Yeah, and again, I
think that was my question also, so thanks for asking. So let me just refine it a little bit.
Yeah.
So I have a little bit of concern when you say that it's easier to do impedance matching for voltage stability rather than tracking the PV curve. I mean, if you, for example, keep a baseline PV curve as your reference, and then do the tracking with respect to, you build the PV curve online with respect to your measurements, and you do the comparison with respect to your baseline, don't you think that's an easier method than to, because what he's asking is that when you draw the system level impedance versus the load impedance, you have to calculate them from online measurements, right?
Yeah,
and that represents the aggregated impedance of the entire thing.
Yeah, and if I want to now dig a little bit deeper, and we can even talk a little bit offline about this, but the methodology started with that simple premise. But of course it has evolved, and we have, for example, the approach we have is a corridor approach. Okay. So there are a corridor approach and there is a load center approach. With both of these approaches, you don't have just two measurements. You actually have much more measurements to be able to really take into account some of the system changes that will be happening. Okay, so with the corridor, let's say assume you have a corridor, you have measurements actually from both sides. Okay, in the load, because that is usually a load phenomenon, you then need to see how load is fed and how many paths actually you have to feed the load to be able to do measurements. You can have actually 5, 6, 7, 8 measurements to be able to really calculate this properly. And of course, the key really is that how to, you assume that your load is changing, but your Thevenin, you cannot assume that your Thevenin will be constant. And to your question is, originally the simple method would say you would assume Thevenin constant, but you need to be able to look into the changes of the Thevenin to be able to really make the accurate calculation. And that's why you have, of course, much more sophisticated equations to be able to do that. So if you look in a way, from your perspective, you say PV, what is PV curve? You measure what? You measure P and voltage. What does this Z Thevenin Z equivalent measures? Basically the same thing. It's just the issue that, and that's what I want to emphasize. I mean, this is all, you always manipulate the same equations. How you can represent them, that's the method that you are developing. So if you go to this, I'll try. Okay. Now, look at the PV curve. Where is the PV curve? I think I showed PV curve here. Okay. These are the measurements. Okay. And this is the real life. This is actually from BPA, Bonneville Power Authority. What you're able to do here, because of the algorithm, and again, algorithm is not only steady state equations, but it's transients. Because you have the noise. You know, how many measurements you need to make, and so on. So if you look here, you're actually able to do, what's this? This is the Q curve, QV analysis. So you are, see, this is the QP curve. And of course, PV curve, QV curve, you have the relationship. Yeah. So what you're doing here, you have your QV curve, you have the, to your points, the boundary, you're calculating the boundary, that would be like calculating PV curve, your base PV curve, and you're now looking what's happening really with the operating points. Yes. So in a way, it's a similar approach. But what is happening here is that it makes you really easy to detect the margin. Because you say, I'm seeing the margin, this is my margin, that's it. I have 160, 140, I knew that was 100. You're getting closer, so you don't now have to worry too much about the PV curve. Remember these dots, they're all over the place. It's simple. So at the end of the day, I'm always a big believer. The most complex thing is should be the one that makes it, or the most important thing is if you can make things simple. And that's really the explanation. Is it okay?
Yeah.
Okay.
But if we move closer to more integration of fact systems, where we start controlling the reactances more,
Right.
do you see that as being a better longer-term approach then?
No, that does not compete with each other at all. And again, I'm sorry, I was probably a little bit rushing here on these details. This is the methodology to detect proximity to voltage instability. Okay, so you have measurements using PMUs or EMS SCADA data that tells you how close you are to the voltage instability point. Now, you need to use whatever means you have in your system to manage if you are approaching voltage instability. So you can turn on fax devices. So what control actions you are going to take, that's the next step. So the more control devices you have on the system, the better it is for us to manage the voltage stability problem. So you'll have your StatComs, you'll have your SVCs, and then they will help you to decide what you need to do. Because do I need to switch my SVC? Do I need to switch on my StatCom? In which area? So, and that's what really it helps you. So it doesn't solve the problem, it indicates where you need to go to be able to solve the problem.
I think that questions has to do because we are going to run out of time. Let's give him another round of applause.
Thank you.